Okay, this is a relatively long commentary on the future of integrated human water system modeling. And they introduce, well, they use some terms that are now around, like convergent and transdisciplinary integration. Convergent science essentially is a fancy word for saying that we cannot worry about water systems as just a physical system which is going to be modeled with a bunch of equations and parameters and focus only on the water budget, conservation of mass, energy, and so on. But you have to actually include land use change, human impacts, and human use, industrial, domestic, and agricultural, and so on and so forth. And transdisciplinary, of course, there are actually formal definitions of inter, multi, and transdisciplinary, but we'll see what they mean here in a minute. So, convergent and transdisciplinary integration on the future of integrated modeling of human water systems. We'll read the key points up front so that if you want to skip the rest of it, because I suspect this is going to be at least two podcasts, since it's a nice long paper and I'm going to cut out a lot of the text, and yet it's going to be two podcasts. Key points then: for transformative research and insight generation, the modeling paradigm needs to shift from predictive to diagnostic and exploratory. Wow, that's kind of a funny statement. Everything we are trying to do is do predictions, but diagnostic and exploratory means you are going to look at what has happened and try to understand the processes involved. Maybe they will be about human water systems. We also talk about human environmental systems. So if you want to be integrated, then you can also call it human environmental systems, but then that loses the focus on water. Exploratory basically means more understanding of basic processes to human water system interactions and feedbacks. Breaking disciplinary barriers requires directing attention to systems complexity rather than computational complexity. So we build models and we start immediately worrying about resolutions, computational costs, and maybe use AI or GPUs and so on. But there are always systems complexities on how the geopolitics. Now, let's say India and Pakistan are having some tensions because of what just happened, and one of the first things to get hit was the water system, right? Shared waters, shared river waters. For successful integrated modeling of human water systems, sensitivity analysis and multi-fidelity modeling are essential. Okay, fine. So maybe that's not as impressive, but they make some good points that we'll just go through. Okay, what's the abstract? The notion of convergent and transdisciplinary integration, which is about braiding together different knowledge systems, is becoming the mantra of numerous initiatives aimed at tackling pressing water challenges. Yet the transition from rhetoric to actual implementation is impeded by incongruence in semantics, methodologies, and discourse among disciplinary scientists and societal actors. So, water is essentially a social, socio-economic, and geopolitical problem, but also obviously a very strong science problem, especially with climate change, extreme events, land use change, and so on. Here we embrace integrated modeling both quantitatively and qualitatively as a vital exploratory instrument to advance such integration, providing a means to navigate complexity and manage the uncertainty associated with understanding, diagnosing, predicting, and governing human water systems. So they are back to predicting, which is a good thing, otherwise it will be irrelevant as far as I'm concerned. From this standpoint, we confront disciplinary barriers by offering 7 focused reviews and syntheses of existing and missing links across frontiers, distinguishing surface and groundwater hydrology, engineering, social sciences, economics, indigenous and place-based knowledge, and studies of other interconnected natural systems such as the atmosphere, cryosphere, and ecosphere. So it's in a earth system context including human systems, so we sometimes call it the natural human system as well. So yeah, While there are arguably no bounds to the pursuit of inclusivity in representing the spectrum of natural and human processes around water resources, we advocate that integrated modeling can provide a focused approach to delineating the scope of integration through the lens of three fundamental questions. What is the modeling purpose? What constitutes a sound boundary judgment? We'll see what that means. What are the critical uncertainties and their compounding effects? More broadly, we call for investigating what constitutes warranted systems complexity as opposed to unjustified computational complexity when representing complex natural and human natural systems, with careful attention to interdependencies and feedbacks, scaling issues, nonlinear dynamics and thresholds, hysteresis, time lags, and legacy effects. So it's pretty much the kitchen sink. So these kind of commentaries obviously throw everything together and try to provide some commentary on what has happened, what is missing, what needs to happen, and how to get there. So they are interesting to read just to see, because I never show the author list, but it's a very long author list, and this journal has high credibility, water resources research. So I take these papers just to give you a sense of what people are thinking about. And this is a brand new paper, so it's quite state of the art in that sense. Why convergent and transdisciplinary integration? So what is the context? I'm just taking bits and pieces. Integrated modeling is a process by which models of different but related systems originating from different knowledge and sectoral domains are connected to enable the exchange of knowledge and the representation of feedback mechanisms across a larger, more inclusive system. Integrated modeling has been subject to extensive research in the past 2 decades for integrated assessment within different scientific communities to address complex problems in human natural systems. Okay. However, the interdisciplinary links in integrated models of social ecological systems have arguably been biased toward biophysical processes, particularly those from meteorology, hydrology, the cryosphere, and ecology, with slow progress on converging towards overarching environmental system theories. You can read that up, literature on that. Extending such a theory to directly include human and policy dimensions is advancing, but needs much more attention compared to the modeling of biophysical processes alone. This extension is hindered by several grand challenges, including the complexity of decision-making processes at individual or institutional levels and epistemological barriers understanding to bridge state-of-the-art social and natural theories. Social science, the problem statements and solutions sometimes tend to be discursive, descriptive, whereas STEM scientists like equations, parameters, statistics, and integrate on a computer and produce numbers and so on. So the two disciplines tend to have very strong barriers in integrating them together. It can happen that you integrate a model, biophysical model as they call it, give the output, and then social science does something with it. But the argument here is that that approach is basically not going to work anymore. We need to integrate them together. More broadly, the significance of transdisciplinary scholarship associated with convergence research or systems integration or post-normal science has been widely recognized across all areas of science and engineering. So these are terms, post-normal and convergence research. I'll show the definitions that AI gives me on those just to get a sense. In a recent workshop of the American National Academies of Science, Engineering and Medicine, convergence was defined as an integration of knowledge and ways of thinking to tackle complex challenges. So they defined this already. Convergence was defined as an integration of knowledge and ways of thinking to tackle complex challenges and achieve new and innovative solutions that could not otherwise be obtained. Okay, very general. The convergence of the life sciences, physical sciences, engineering, and social sciences has been referred to as a revolution in some areas of research. So, water is indeed something that requires all these integrations. As a result, research funding agencies are increasingly paying attention to convergence. For example, growing convergence research has been one of the 10 big ideas of the National Science Foundation in the US since 2017. But as you know, right now, NSF is having massive problems with fund cuts and so on. In this context, integrated modeling is often deemed a well-established framework to tackle the challenges associated with convergence and transdisciplinary scholarship. So, convergence science, let's read another definition, is a research approach that emphasizes integrating insights and methods from various disciplines to tackle complex problems, particularly those with societal implications, and nothing is more societal than water. It moves beyond traditional disciplinary silos by bringing together diverse researchers to develop new frameworks and perspectives. The goal is to find solutions to challenging issues by leveraging the strengths of different fields and fostering collaboration. Post-normal science is a problem-solving strategy developed to address issues characterized by high complexity, uncertainty, and the need for broad stakeholder involvement. So, said in a different way but similar. It's particularly relevant when facts are uncertain, values are in dispute, stakes are high, and decisions urgent, which is what climate change impacts and solutions tend to be. Often these are seen in policy relevant research according to Wikipedia. Post-normal science contrasts with traditional normal science, which often focuses on puzzle solving within a well-defined framework, says the International Society for Ecological Economics. So, let's say we are focusing on El Nino or monsoon or some other problem. We are always looking for using models and data and looking for how things are changing at all time scales, what are the statistics of extreme spatial distributions, temporal changes, and so on. Whereas the post-normal science would focus on basically also looking at how all these things, changes and natural variabilities, affect stakeholders, and how one would go beyond just process understanding into actually predictive understanding, as well as predictions designed for specific stakeholders. Okay, so by moving away from reductionism toward convergent and transdisciplinary integration, we aim to shift our focus from using models to assert answers to using models as a means to explore questions, diagnose systems, and possibly discover new questions which might have historically been overlooked but are crucial to ask. This shift is at the heart of the philosophy of exploratory modeling, which relinquishes the ideal of a model as a predictive tool that turns the best available knowledge into the best estimate of the future state of a system. Okay, so there are some other details here, but let's just jump ahead. What do they want? We contend that historical advances in integrated modeling have predominantly concentrated on technical, software, and implementation aspects, but significant work remains to address the semantic, epistemic, and conceptual challenges of the integration problem. Fair enough. What are the ponderings of this team? What system components and processes need to be modeled for the problem in question? What level of fidelity, that is realism in terms of detail and complexity, is necessary for each model in terms of process representation and space-time scales? How should the various models interface with one another? So, in a sequential, modular, two-way coupling manner to build the integrated model. How should uncertainty be handled in each model and in the integrated model as a whole? I'm getting a phone call here. Give me a second. Okay, there's going to be another call because somebody is going to come knock on the door, but I'll continue till they come. So we're looking at the kind of questions that the team ponders about. How should uncertainty be handled in each model and in the integrated model as a whole? How should the modeling process be conducted to engage societal actors to maximize the capture of relevant knowledge and enhance the value of integration? So in the present paper, we recognize that the holy grail of integrated modeling is to find an optimal level of complexity and fidelity with an accurate characterization of uncertainty. However, we believe that this aspiration can be reasonably approached for a given problem through careful deliberation among the parties involved in the social process of integrated modeling, guided by three fundamental questions as outlined in the following section. So maybe I should stop before I get disturbed again. This is almost about 15 and a half minutes. So let's go for a couple of minutes till they show up. The three overarching questions, let's read up the front material. Before embarking on the what and how of integrated modeling, it's important to take a step back and consider three fundamental questions that can be overlooked or treated lightly. Why do we model? What is a sound boundary judgment for a given purpose? What are the critical uncertainties relevant to the modeling purpose and boundaries? Addressing these questions at the outset ensures that the modeling exercise is well conceived and aligned with the problem at hand. Therefore, let's first revisit these questions and reflect on their implications. Why do we model? Obviously, we are going to do nowcasting, forecasting, scenarios for the future, what if scenarios, and also process understanding. What is a sound boundary judgment for a given purpose? Boundary judgment relates to what is to be mathematically represented as a relevant component within a model, that is, the assumptions about what is inside versus outside the model. For example, in traditional hydrological modeling, processes governing how soils restore and release water are deemed endogenous, whereas processes governing precipitation formation or vegetation dynamics are exogenous, that is, only affecting the model through boundary conditions. I think there is somebody at the door, so let me stop again. Sorry about that. Nobody at the door, it was a neighbor. But anyway, so boundary judgment is critical because you do have to decide what all you are going to include. Even though we mentioned a lot of things that need to be integrated, in reality you are going to have a problem to solve, let's say a river basin level work, or a national boundary level work, or international sharing questions, and so on. So most hydrological models used to assess the impact of climate change on water resources overlook the impact of the vegetation's response to climate change on evapotranspiration and thus runoff. Not necessarily true anymore, dynamic vegetations and so anyway. Cryospheric processes may be considered both endogenous and exogenous in hydrological models depending on their assumptions about the hydrological system and inclusion of cold region processes. Typical of India's rivers, many originate in the Himalayas, but cryosphere is not necessarily included in an integrated sense. Boundary judgments may even dictate the details of internal aspects of a model, such as the time and or space scales at which processes are represented. For example, water management models are typically run at a weekly or longer time resolutions, but if hydro peaking in a water management problem is of interest, the model will also need to represent the sub-daily reservoir releases that are used to meet peak daily electricity demand. So you are now combining energy and water, but also many of these models require data. So reservoir operation and irrigation data is pretty much unavailable. People try to infer them, but if you really want to do sub-daily peak daily, sub-daily variability for electricity demand, then somebody has to give you the data in near real time. Otherwise, you're not going to be able to manage it. What are the critical uncertainties relevant to the modeling purpose and boundaries? Okay, so uncertainties are mentioned a lot, but it's not always easy to quantify them. So the case of flood frequency analysis in the design of water infrastructure is a good example. What kind of uncertainties can you tolerate? Resorting to probability theory has provided a pragmatic approach to tackle water systems problems that are complex, open, non-stationary, and only partially observable. This approach, however, may have limitations when applied to integrated modeling problems, but on the other hand, infrastructure will have safety factors and they may naturally include uncertainties as just a safety factor. Okay, because there are many examples where you will always have uncertainty. Post-normal indeed means that you have to work with uncertain situations and yet provide some decision support. So the model has to serve that purpose and not always obsess about quantifying uncertainty, because there may be irreducible uncertainties as well. Okay, so these guys haven't come yet, so let's continue. Convergence frontiers, they identify many convergence frontiers that need to be addressed in integrated modeling. With a hydrology-centric view of convergent and transdisciplinary integration, we contemplate the existing and missing links across hydrology frontiers with engineered works and social systems more generally, including socioeconomics, cultural flows, and stakeholders, including indigenous rights holders, and their knowledge, as well as other interconnected natural systems, including the atmosphere and cryosphere. So we'll look at one schematic in a minute. While groundwater is an integral part of the terrestrial hydrologic cycle, we have dedicated a separate section to its unique challenges, the terrestrial hydrologic cycle, which is obviously a big part of the human water system. We also recognize that although environmental flows ideally demand a deep integration with ecosystem sciences, the reality often involves water engineers making pragmatic decisions shaped by societal perspectives. So they often cater to domestic agricultural and industrial uses and not so much ecosystems and their role in the overall water system. To address this need, we have devoted a section to the synthesis of water quality, ecosystems, and cultural flows, promoting a more integrated understanding of these interconnected elements. So these are all there in detail. I'm obviously going to skip a lot of the details. So here, a summary of the convergence frontiers with surface hydrology and associated challenges that are discussed in this paper. Cryosphere, obviously snow, soil representations, data scarcity, permafrost, shifting regime of river ice. Atmosphere, we know all the problems: vegetation cover, land use, near 0 degree precipitation, climate effects of water management. So lots of literature on climate and water, and atmosphere is a big part of it. Water quality, ecosystem, and cultural flows. So obviously health comes in there as well. Intricate water quality links to hydrology, complex ties to ecosystem health, subjective environmental flow definitions, cultural flow underrepresentation. Socioeconomics, scale mismatch with hydrology. So obviously the integration even in a river basin into a river or other forms of water, it could be groundwater or surface water, the demands, populations, demographics, sharing, etc., can be very different scales compared to the basic processes of hydrology. Impacts beyond water using sectors, feedbacks, and Jevons paradox. Jevons paradox is where efficiency goes up but use goes up because people think we are being very efficient. Global trade considerations and water resources engineering, we know what they are. So they obviously want to just manage water and meet the user needs. Indigenous knowledge, any solutions that come in from outside or think only global scale and ignore indigenous knowledge and indigenous existence with the water bodies over long times end up failing in many cases. They have to be stakeholders and co-developers of any solution. And of course, groundwater can again have scale mismatch with surface processes because they are underground reservoirs that take a long time to recharge. Sorry, I just missed the word. long time to recharge, but you can mine groundwater at meters per year by just sucking them out. Lagged response, mining it. Lagged response to stressors, trust issues from partial observability, limits of groundwater quality and research. So these are always big problems when you're trying to share things. Okay, so just kind of touching on these things in the same section on convergence frontiers, we have things like water resource engineering, socioeconomics, and so on. I'm here already about, sorry for all the interruptions, 25 minutes, so I'll keep going till these guys actually knock on my door because they're taking their time. Somebody calls and says they're coming right over, but then you know that doesn't mean anything. So I will keep going. I'm giving all this commentary because I'm dealing with this in real time. How water resource engineering, how can we configure a hydrology model for heavily regulated watersheds, including reservoirs and irrigation? How does a change in hydroclimatic regime affect water management? How do water diversions and irrigation changes change the evapotranspiration and runoff regime in a basin? How can a reservoir attenuate or amplify flood risks under climate change and new extremes? So each subsection has a long discussion that I'm skipping. Socioeconomics, what are the economic impacts of changes in availability and timing of the flows? How may water shortages due to climate change or policy change affect non-water using industries? How may intersectoral and cross-regional transactions control water demand and management? Obviously, you can make up many questions. These are not necessarily comprehensive, exhaustive, nor necessarily the most prioritized if you ask me, but it's a team that works together and decides on these, and then there is a review process and reviewers say something. So this is what you get on a published form. Water quality, ecosystem and cultural flows. How can water quality dynamics be integrated into large-scale human large-scale models, hydrological large-scale models, whatever it is. I missed the acronym there. How does a change in river flow regime due to climate change or water management affect the health of the aquatic ecosystems and so on? Indigenous and traditional knowledge. How can water management uphold indigenous values of water and the environment? What can the knowledge and experiences of indigenous communities offer for integrated modeling and vice versa? And of course, groundwater. How resilient are groundwater systems to stresses and what signals their failure? So Northwest India is always used as a showpiece for how agriculture is being driven by extreme groundwater mining. Even when the monsoon is normal, irrigation keeps going on, so groundwater levels are dropping precipitously, and recharge is obviously not happening that fast. Which rivers, lakes and wetlands depend on groundwater for flows and quality? What are the ecological, cultural and economic impacts of groundwater abstractions? At what extraction volume does groundwater quantity and quality reach a tipping point? Which is always a word that is used without saying what the tipping point. What does it mean in this case? Obviously that means you cannot get any more water for any useful purpose anymore. You have exhausted it and you have to just wait for geologic times maybe to get for the aquifer to groundwater to get recharged. How does climate change impact groundwater resources and with what timeline? This is a good question because rainfall redistribution and extremes are happening, and groundwater, land use is happening, urbanization, agriculture, deforestation, etc. How are they all working together to affect groundwater recharge, right? How much complexity must be included for an adequate representation of the groundwater system for integrated modeling? Groundwater is not typically included in many of the hydrological models depending on what the purpose is, but people have modules of groundwater they then couple, but the scale mismatch and the time scale mismatch always makes it tricky to carry them together. Okay, so let's read atmosphere as well. How is evapotranspiration affected by the response of vegetation to climate change? So ecosystem feedbacks, soil adaptation and feedbacks between irrigation and micro and macro climates, Irrigation is now blamed for changes in temperature trends, in groundwater recharge, heat waves, and so on and so forth. But the actual land atmosphere interactions and energy balances, precipitation, storms, how do they get affected by soil moisture and irrigation and so on? Those are all critical questions. Uh, how do seasonal, so cryosphere then, how do seasonal and long-term changes in snow, river ice, frozen soils, permafrost and glaciers interact with the hydrological systems? How will climate change, which reduces the cryosphere, impact hydrology, water management, ecosystems, and socioeconomies? How does snow's interaction with shifting vegetation dynamics affect its redistribution and sublimation? Does reduced mountain snowfall and increased rainfall runoff lead to less efficient runoff generation mechanisms? So basically very general questions, and you can add many more, I'm sure. But the point is that many times we are looking at them separately. For example, cryospheric losses in mountains and other sources for river waters are being looked at, and they are focused on, let's say, mass balance and snow lines and other things, but not necessarily integrated with the rest of the hydrology or the kind of questions if there is deforestation happening or development on mountain slopes, which is changing vegetation dynamics, soil dynamics, and snowfall is maybe changing into rainfall because of warming. Then all these are going to add eventually to the river runoff, production process, time scales, and flood risks and other things. So how do you integrate these things? Talking about time scale mismatches, cryosphere is even much slower than many other processes in the system. So how do you match the scales, and how do you decide the boundaries where your model begins and ends? So it's tricky, but anyway, let me stop this podcast here. As I said, it will definitely take at least one more. Despite the stops, I think I'm over 30 minutes anyways. So let's come back and conclude the rest of this commentary on transdisciplinary and convergent modeling of integrated human water systems. As you can see, these are mostly general points, but they are useful just to add the commentary on what are the issues that we are dealing with, just from hydrology side, from the climate change side, from the human activity side, and so on. Okay.